We are now in the final leg of this course on real analysis. In this part of the course, we shall study the Lebesgue integral. The Lebesgue integral behaves very well with respect to limits. Recall that we have already shown that if a sequence of functions that are Riemann integrable converge uniformly on an interval, then you can interchange the limit and the integral. But this requirement of uniform convergence makes the Riemann integral not so well suited for many applications in analysis and outside. The Lebesgue integral remedies this deficiency of the Riemann integral. There are several approaches to the Lebesgue integral. Henry Lebesgue created the Lebesgue integral using his concept of Lebesgue measure, which was part of his PhD thesis. Subsequently, there are several other equivalent formulations of the Lebesgue integral that bypasses measure theory. We shall use one such approach popularly attributed to the mathematician Ries. We shall closely follow the treatment given in Apostol's mathematical analysis. But before we get ahead with the actual nuts and bolts, let me try to motivate how this Lebesgue integral can be viewed in light of the theory we have developed for normed vector spaces. To do that, we will revisit the Riemann integral from the perspective of completion and extension of linear maps. So, recall that for the Riemann integral, we partitioned the interval AB and considered upper and lower sums. Then we sort of refined these partitions further and further, and we said that the Riemann integral, the function is Riemann integrable on the interval AB if the upper sums and lower sums can be made as close to each other as you desire by making the mesh of the partition suitably small. Now we are going to view this Riemann integral in a slightly different way. Let us start with a step mapping. What's a step mapping? Well, a function f from AB to R is said to be a step mapping or function, is a step function or map if there is a partition P of AB. Recall, a partition is just a collection of points from the interval AB. We usually denote the partition like this: A equal to A0 less than A1 less than A2 ... less than AN, and this AN is equal to B. If there is a partition such that F restricted to the open interval AI plus 1 is constant, where I runs from 0 to n minus 1. So you can break up the interval AB into finitely many pieces such that on each piece the function is constant. Note that the values at AI are irrelevant. It could be anything. Are irrelevant. Okay, so for a picture you have, let's say this is our interval AB, then you have this partition. In each one of these sub pieces this is sort of constant. So that's what a step function is. At these endpoints it could be anything. It could take values that are very different at the endpoints. It really doesn't matter. Okay, now of course from the theory of Riemann integral that we are now very familiar with, it's clear that the integral of a to b of this step mapping f is nothing but summation of wi into ai plus 1 minus ai. I runs from 0 to n minus 1, where wi is the value of f restricted to ai comma ai plus 1. This is easy to see if you are familiar with the Riemann integral. This is rather trivial. In fact, this also says that the Riemann integral of a step function, of course, is the sum of the areas of the various rectangles that are formed by the values of the function f. This is one rectangle, this is another rectangle, this is a third rectangle, so on and so forth. Okay, signed sum, of course. So instead, so let's give this equation a name. Let's call this star. So this integral a to b f being equal to this already presupposes that you are familiar with the Riemann integral. But what you can do is you can make this into a definition. That is, we can define integral a to b f by star. Right? For a step function, we can define the Riemann integral to be given by this formula. Of course, there's something to check. So that will be the first proposition. This is well defined. This definition is well defined for step functions. And the proof is rather easy and should be familiar to you. I should remind you of several of the arguments we have done when we studied the Riemann integral in real analysis 1. Okay, so let f from ab to r be a step function, step map, and let p subset of ab be a partition such that f is constant on the subintervals determined by the partition. Now the standard trick that we are going to use is we have to show, what is the meaning, what possible issue could arise in this definition is f is a step function. There is no unique partition p such that f is constant on the subintervals determined by p. There could be millions of them, right? We just know that there is one such partition. How do you know that this sum star is going to be the same irrespective of the choice of partition you make? Well, what we are going to do is, suppose we add one point C to this partition. Now I'm going to show that when you add this one point, the integral is not going to change. Then by an induction argument, you can prove that no matter how many points you add, the integral is always going to be the same. Then if you have a step map which is constant on the subinterval determined by another partition q also, then you just take the common refinement and you are done. You have shown that the integral defined with respect to this formula for the first partition p is same as the answer you get when you use the same definition for the partition q. Okay, so what happens if you add 1 point? Well, suppose the original partition was a0, or rather a equal to a0 less than a1 less than ... less than an equal to b. Well, let's say between ai and ai plus 1 we add this point c. So we have a equal to a0 less than a1 dot 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 less than ai. We add a c in between here, less than ai plus 1 less than dot 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 less than an equal to b. In one of the subintervals we have added a single point. Well, what is star with respect to this new partition? What is star evaluate to? Well, if I choose the value, so let wi be the value of f restricted to ai comma ai plus 1, then what does star evaluate to? Well, it's the same as summation. Let's not write a summation, let's just keep it as w1 into a1 minus a0 plus dot dot dot. Then what will happen is when you reach this interval ai plus 1, the crucial part where a point has been added, in fact the only place where something has changed, what will happen is you will get two terms. You will get wi into c minus ai plus wi into ai plus 1 minus c plus wi I plus 1 ai plus 2 minus ai plus dot 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 wn wn minus 1 an minus 1. Okay, so technically this should be w naught. This should be w naught by our notation. Okay, excellent. This is nothing but summation wi into ai plus 1 minus ai. These two terms just combine together, and this is just equal to star with respect to the partition P. Okay, so adding one point to the partition does not change the value of the integral we have defined for step mappings. By induction and taking common refinement, it is clear that star is well defined. I will not belabor this proof anymore. It should be clear to you what is happening, and you have done such proofs quite a lot when you studied the Riemann integral as part of Real Analysis 1 or elsewhere, wherever you picked up the Riemann integral from. Excellent. So we have shown that this star is a good definition for the Riemann integral for step functions. Now here is the crucial point, and this is sort of like an exercise, an easy exercise. Denote STAB to be the collection of step maps f from closed interval AB to R. Then STAB is a normed vector subspace of B AB R, that is the set of all bounded functions on the closed interval AB to the real numbers with subnorm. This is a rather trivial exercise. All you have to show is sum of two step functions is a step function, a scalar times a step function is a step function, and the fact that any step mapping is bounded and all that. Okay, so this is a rather trivial exercise. So the collection of step mappings is in fact a normed vector subspace of the set of all bounded mappings given the subnorm. Okay, now another lemma which is almost immediate once you prove this exercise, it will be rather easy to define, easy to prove. So denote by IAB of f in STAB to be the integral given by star. The integral given by star. Then IAB from STAB AB to R is a continuous linear map, linear functional. That is a bounded linear functional in the terminology that we have developed in the first part of the course on metric spaces. Well, the proof of this is not so hard. Proof. Linearity is trivial. That just follows from the definition. And taking refinements, linearity of star or linearity of IAB. How did I put it? IAB. IAB is trivial. As for continuity, well, observe that if supremum of, or rather norm F under the sup norm is some m, then star immediately gives IAB of F is less than or equal to m times b minus a. Okay, so which immediately proves continuity, which gives continuity from the theorems that we have developed about continuity of linear maps on a normed vector space. So we have defined an integral not on all continuous functions or all Riemann integrable functions, but on a very simple set of functions, the set of all step mappings. On that we have defined an integral that obviously agrees with the classical Riemann integral that we have defined in real analysis 1. But this IAB is linear on the space of all space of all step mappings. Well, the next step is the definition. Let F be an element of ST AB AB closure. We define IAB of F to be the value of IAB on or rather let me just state it in a slightly different way. Let me define it in a slightly different way. This is a bit complicated. Let the space, let's call it C. Let the space C be by definition ST AB closure. Okay, now C is a closed subspace of the bounded functions from AB to R. Since R is complete, IAB extends to be a continuous linear map. Denoted again by IAB. Again. That is, we don't introduce another notation just to burden ourselves. IAB extends to be a continuous linear map denoted by IAB again. Then the definition is IAB of F is said to be the Cauchy integral of F, which is there in ST AB closure. Elements of this ST AB closure are called regulated maps. Okay, let's take a deep breath. What have we done? Well, defining the Riemann integral as the area under the curve is rather straightforward and trivial to do for step mappings. There's no complication that arises. So we do that. That was stage 1. Then we exploit the advanced machinery of normed vector spaces and linear mappings on them and extensions on them to immediately extend the definition of that integral to a much larger class of STAB closure. Now, it will turn out that every single continuous function is actually there in STAB closure. I will not be proving that in this course. You can check Lang's undergraduate analysis for details. Undergraduate analysis for details. Since we have already spent the time developing the Riemann integral in the classical way, I will not do it once again using these step mappings and taking the closure and linear extensions. This is just to prepare ourselves for what is about to come as part of the Lebesgue integral. So, using this abstract machinery of linear extension, we have managed to get an integral defined on a substantially good class of functions, STAB closure. It will contain all the continuous functions, for instance. It will also contain plenty of non-continuous functions. In fact, most step mappings are not continuous. And what is so special about this approach is proving the basic properties of the integral for step mappings is rather trivial. In fact, I just left it as an exercise, show that it's linear and all that. It's rather easy to do. What you can do is exploit this fact that this IAB comes from a linear extension to get many of the properties of the Riemann integral almost for free. We did quite a bit of hard work when we proved the basic properties of the Riemann integral. You can sort of get all of those for almost free if you take this approach. One disadvantage of this approach is it's quite non-constructive in the sense that you are appealing to quite an abstract theorem on normed vector spaces to even define the integral IAB of f. But nevertheless, as a theoretical reformulation of the Riemann integral, this is quite useful, and one can justifiably define this integral as the standard integral and forget about the more technical construction using upper sums and lower sums. It's purely a matter of popularity. The older construction is still more popular, but many people do believe that this abstract construction is the correct one. But nevertheless, leaving aside the controversial points regarding pedagogy, coming back to what we are about to do, we are going to be inspired by this approach. Define the same integral for step functions, but this time take a different sort of limit. Here we are sort of taking, when you take the closure under the sup norm, that's same as uniform convergence. So here we are taking sort of the uniform limit of functions and calling those the regulated functions. Instead, we are going to consider a different sort of limit and define a new integral, and that new integral will be much more powerful. The collection of all such integrable functions will be a much bigger class, and it will behave well with respect to taking limits. Okay, so for the interested student, you can refer to Lang's undergraduate analysis for all the details of how to recover all the basic theorems that we have proved for the Riemann integral for the Cauchy integral, and also contrast the two approaches. But that is up to you. That's not part of the syllabus of this course. In the next video, we shall talk more about step functions and monotone sequences of step functions and prove a certain limit theorem for such sequences. That will pave the way for eventually defining the Lebesgue integral, which, as I have repeatedly said, is a substantially more powerful integral from the perspective of analysis. This is a course on real analysis, and you have just watched the video on the Riemann integral revisited.